In this video, I'll be showing you how to use the trapezoid rule to numerically integrate a function. And before I proceed, I recommend that you copy these tables down here, or you can also download this Excel file, which I've shared in the description below. And this is just so that when we input values or formulas throughout the video, it makes it much easier for you when you want to do so. Right, so here we're given our problem, which is to integrate the function 5 plus 3 cos x. And we have the integral that we're asked to integrate from 0 to 5. We're also given the trapezoid rule formula over here. We have several tables with a different deltas, so delta equals 5, delta equals 2.5, delta equals 1, and delta equals 0.5. Now you might find this a bit confusing for now, but I'll be explaining what these mean throughout the video. But let's just start with filling in the first table and utilizing the trapezoid rule. So what we first have to do is evaluate this function here at the 2 points we want to integrate at, 0 and 5. So it just simply means taking this function here and replacing the x here with our x. So taking the x and replacing it with 0. And we do the same for the bottom, where we just replace the x in the function with 5. And afterwards, we can just use the trapezoid formula, which is x, this, minus x minus 1, multiplied by f of x minus 1 plus f of x divided by 2, like this. And there, that's it. We've just used the trapezoid rule, and we got the integral of the function, which we found to be 34.627. Now the thing is, if you use a calculator, which you can check for yourself, the actual value, or the analytical value, is 22.123. But our approximation using the trapezoid rule gave us 34.62, indicating a 57% error. Now, why would the error be so big? And this is why it's important when you numerically integrate or use a formula like the trapezoid rule that you integrate with a smaller step size. And here we're integrating with the largest step size possible, meaning we're integrating directly from 0 to 5. Now what you can do is you can integrate from 0 to 2.5 and then 2.5 to 5 and take the sum of those integrals and then find the actual integral of this function. So if we put this into practice, it simply means, let's just copy these down. Right, again, we're just doing the same thing here, evaluating this function here with the x's like this. And let's find the integral of the function, which is, again, implementing the trapezoid rule here, is x minus 1 multiplied by f of x minus 1 plus f of x divided by 2. Okay, and we can we copy these formulas down. And because first we're integrating from 0 to 2.5, and then we want to integrate from 2.5 to 5, like this. And make sure you don't integrate to the last row, and because you'll get a hashtag value exclamation mark, and that's because when the formula copies down, it integrates from this point to this point, and clearly there's no number in the final row here, and hence it will give you an error. Anyhow, right, we've already integrated to 5, so this is enough. And by using a smaller step size, or a step size of 2.5, we got the integral 23.805. So the exact value is 22.123. We got 23.8, indicating an 8% error, which is extremely smaller than our first example here, using a step size of 5. And I have some graphs prepared to show you why this is, so here. But let's just proceed with these other tables here for now. Okay, and so let's just copy this down here and copy all the functions here, right? If you want to check, it's all the same thing. And here we're integrating with a step size of 1. So let's just copy the integral formula like this and put it here, and there you go. We get an integral of 22.36, right? And the exact value is 22.123. This indicates a 1% error, which is an even smaller error than our step size of 2.5. Now let's see what the value is if we integrate using a step size of 0.5. let's copy the formula down here, like this, and let's copy the integral formula. So let's take that there, and let's copy that down, like this. Right. Just to show you again what we're doing, let's make this like this. Just to show you again what we're doing is we're basically integrating from 0 to 0.5, and then 0.5 to 1, 1 to 1.5, so on and so forth. So we're integrating part per part, and then we're summing up the total of all those integrals like this to get the actual value. And what you notice here is if we use a step size of 0.5, we find that the value is 22.18. Now the actual analytical value is 22.123, and this indicates a 0.3% error, which is smaller than any of the previous step sizes. Meaning, if we want to actually get the most accurate results, we have to use the smallest step size possible. I mean, you can go from 0 to 0.01 to 0.02 and so on, but of course that's going to be it's going to take too much time. But I think for now this is very enough, and it shows you the point as to why we have to do this. And let's just jump into this graph here real quick. So basically what we're doing when we integrate is we're trying to find the area under the curve, right? We're integrating from 0 to 5, and hence why we want to find the area of this yellow highlighted part. Now what we do with the trapezoid rule is basically we're making these small trapezoids which calculate the area for us, right? And so we're taking the area of each of these trapezoids. So take for example here 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. And then we're taking the areas of each of these trapezoids and adding them all up to find the area under the curve, which is what we're doing. Well, what you notice here is that there's some white spaces, which means that some of this area is unaccounted for. And that's just because of the shape of the trapezoid, right? If you think about it, a trapezoid can't cover completely all of the area, since the area goes like a squiggly line. And notice that this is with a step size of 1. Now let's see we use a step size of 0.5. The white spaces are much smaller, and this indicates that more area under the curve has been covered, and hence why the results are more accurate. So let's just take a notice of this portion here, compare it to the previous one here. Notice that there is more white space when we use a bigger step size, and hence why we want to use a smaller step size to get more accurate results. Right, I think that is it for this video. I hope everything is clear. I have some other videos on other numerical methods, such as the fixed point, false position, Newton-Raphson, and so on. So if you're interested, please check those out as well. Yeah, thank you for watching.